Hi guys, hope you all stay safe. In this video, we'll see what a counter is in digital context, basic concepts of counters, types and working. Particularly in this counters, part 1, we'll see asynchronous counters, especially up and down counters. In our syllabus, we have mod 16 ripple counter. But before getting directly to mod 15-16 counter, we should learn the basic concepts of counter, its basic building blocks, etc. First, we'll see what a counter is. A digital circuit which is used for counting pulses is known as a counter, right? A circuit which is used for counting pulses is known as a counter. A counter is a sequential circuit. Hope you all remember what a sequential circuit is, right? Yes, circuits whose output depends not only on the present combination of inputs but also on the past outputs are called sequential circuits. A counter is driven by a clock, can be used to count and store the number of times an event occurs. Example, counters, digital counters are used in circuits to count for counting purpose, and they can count specific event happening in the circuit. And finally, digital counters are made up of flip-flops. And next, now coming to the basic building blocks of a counter. As I said earlier, digital counters are made up of flip-flops. We have seen various types of flip-flops like RS, D, JK, T and master slave, etc. Among these flip-flops, the three flip-flops, namely JK, T and D flip-flops, are used to build counters, right? The three flip-flops are used to build counters. The JK flip-flop is the most versatile and widely used flip-flops. The most prominent reason behind using it as a counter is its toggle operation. Hope you all remember the last combination in the truth table of the JK flip-flop, right? Hope you can recollect that if J is equal to 1 and K is equal to 1, the output complements the previous output. Whatever the output may be in the previous state, now under this condition, the output is complemented. Okay. So just thus, it also works as a T flip-flop, toggling between the states when J and K are tied together and held in high condition. The key to proper operation of a flip-flop is to trigger it only during the signal transition. That is, only during the signal transition. There are two types of transitions. The first one is from 0 to 1, which is called positive transition and also defined as positive edge triggering or rising edge triggering. The circuit is shown in the figure where J and K are tied high and the clock is given. The output responds to the positive edge of the clock, that is the rising edge. Whenever the clock rises from 0 to 1, the output responds and complements its state. This is the positive edge triggering. And the negative edge triggering is when the clock transits from 1 to 0. It is also called negative edge triggering or negative transition or falling edge triggering. Here in the diagram, we have shown a bubble right in front of the clock, which shows that it is negative edge triggering. This is the symbol of the negative edge triggering. Here in the timing diagram, we have the output responding to the negative edge, that is the falling edge. Whenever the clock falls from 1 to 0, the output responds. So this is the negative edge triggering. Now we'll see various types of counters. We have got two types of counters, namely the first one is the synchronous counter, and it is also otherwise called ripple counter. The counter in which the external clock is only given to the first flip-flop is called a asynchronous counter. The flip-flop and the succeeding flip-flops are clocked by the output of the preceding flip-flops. Okay. So, but in the case of the synchronous counter, which is the second category, all the flip-flops are controlled by a common clock, where all the flip-flops are driven by the same clock pulse simultaneously. This is in case of asynchronous counters. Next, coming to ripple counters. So ripple counter is also named as asynchronous counter, or otherwise it is the other name of asynchronous counter. It got its name because the clock pulse ripples through the circuit. Like how the water ripples when a stone is thrown into a calm water storage. No, you might have noticed that water rippling out when a stone is thrown into a calm water, like in a pond or a river or any well or tank, whatever it may be, right? So it is a ripple counter. An n-bit ripple counter contains n number of flip-flops. It contains n-bit ripple counter contains n number of flip-flops, and it is otherwise called mod n counter or a mod n counter or a divide by n counter. The circuit can count up to 2 power n values, that is from 0 to 2 power n minus 1, and it resets to 0. For example, a 2-bit counter where n is equal to 2 counts 4 values 0, 1, 2 and 3. Then coming to various types of counters based on its circuitry, we have got up counter which counts in ascending order, the down counter which counts in descending order, up bar down counter where the counter values either counts in the forward direction or in the reverse direction. And finally we have ripple BCD counter wherein the counter counts the BCD values, that is 0 to 9. So now coming to a 2-bit ripple counter, let us see an example where we have the 2-bit ripple counter. So in the 2-bit ripple counter, as n is equal to 2, we have 2 flip-flops J0, K0, J1 and K1, where this output Q0 is the LSB and Q1 is the MSB. Here the clock pulse, that is the symbol of the negative edge triggering, the external clock pulse is given only to the first flip-flop, and the output Q0 of the first flip-flop drives the clock of the next flip-flop and the second flip-flop. And the timing diagram shows that the Q0 responds to the negative edge of the clock, that is the external clock. Q0 responds to the negative edge of the external clock. See here, it responds to the negative edge of the external clock, but the second flip-flop, that the output of Q1 responds to the negative edge of Q0 and not the negative edge of the external pulse. The Q1 responds to negative edge of the Q0, and thus it counts from 0, 0, 0, 1, 1, 0 and 1, 1, and again it goes back to 1, 1. So similarly, we have got 4-bit ripple counter which is there in our syllabus. It is the other name of a mod 16 ripple counter. We have got the circuit here of a 4-bit ripple counter or mod 16 ripple counter where the negative edge triggering is applied to all the flip-flops. We have got 4 flip-flops J0, K0, J1, K1, J2, K2, J3 and K3. here the external clock is given to the first flip-flop. So Q0 responds to the negative edge of the external clock pulse. Then Q1 responds to the negative edge of Q0. Q2 responds to the negative edge of Q1 and Q3 responds to the negative edge of Q. So this is how the 4-bit ripple counter works, and it counts from 0, 0, 0, 0 to 1, 1, 1, 1, that is 0 to 15, and again resets back to 0. Then again coming to down counters, just like ripple up counter, we have got binary 4-bit down counter. This counter starts from 1, 1, 1, 1, counts down for each clock pulse and reaches 0, 0, 0, 0 finally. This arrangement for 4-bit binary down counter with its corresponding waveforms and truth table are shown over here. A 4-bit binary counter can be constructed using 4 JK flip-flops. Here, what we are doing is we are taking the output from the high Q0, Q1, Q2 and Q3, and we are giving the output Q0 bar to the next flip-flop, second flip-flop, Q1 bar to the third flip-flop, Q2 bar to the fourth flip-flop, right? So instead of taking the output from Q0, we are taking the Q0 dash, we are taking the output from Q0, Q1, Q2 and Q3. But we are giving the clock pulses, taking the output of Q0 bar, Q1 bar, Q2 bar and Q3 bar for the next stages of the clock, right? So when Q0 is toggling from 0 to 1, this Q bar will toggle from 1 to 0. When this Q0 goes from 0 to 1, Q0 goes from 1 to 0. This acts as the negative transition for the second flip-flop. Okay. So likewise, when Q1 goes from 0 to 1, Q1 bar goes from 1 to 0. This again acts as the negative transition for the third flip-flop. Likewise, it counts. Initially, all the 4 flip-flops are preset to 1, 1, 1, 1. So here Q1 responds to positive edge of the external clock pulse. Q2 responds to the positive edge of Q1 and Q3 responds to positive edge of Q2. So this arrangement gives a down counter, right? Here the counter comes from 1, 1, 1, 1 to 0, 0, 0 and back to 1, 1, 1, 1. So this is all about the down counter, and we will see you again in counter part 2. Bye.